Okay, let's review what we learned last week. Okay, last week we talked about some of the multiple access schemes. Frequency division multiple access, TDMA, CDMA, SDMA, right? We're going to look at one by one. This picture basically shows you a basic concept of FDMA, TDMA, CDMA. And as you can see here, we have a time domain, time axis, frequency axis, and this is a power. And FDMA is like you allocate some different data or different users over the frequency domain. Whereas in TDMA, you can use, maybe each user can use a wide bandwidth, but the users, or maybe it's a different data stream, is separated by time. Okay, each one we call it as a time slot. So this one is the minimum unit of scheduling or data allocation. That's called the time slot. Okay, so in time axis we divide it by time slots. In frequency domain, we typically assume a narrow band because we divide users by the frequency. Okay, and CDMA is something different. Everyone use the same time and same frequency. They all overlapped. The way to differentiate the user is based on the code. Okay. Before we talk about that, the multiple access schemes, we first have to briefly talk about the duplexing for each user. There are generally two different ways, FDD and TDD, right? Duplexing basically means that how to transmit, how to receive. So frequency division duplexing was like you use the two different frequencies for forward and reverse, right? Forward is same as a downlink, reverse same as uplink. Okay. So for user perspective, this is a transmission, this is a receive. Okay, reception. And you use two different frequencies so that you can do the full duplexing. When you transmit, you can also receive at the same time. Whereas in TDD scheme, it's like a walkie-talkie. When you transmit, you just transmit, you cannot listen. And when you listen, you should not transmit. Okay, just this is also like a similar concept as the TDMA. So each of these time unit is called a time slot, or sometimes called the mini slot. And this is divided. The time axis is divided by these time slots. So they just take turns, transmit, receive, transmit, receive. Sometimes, if necessary, then if you want to receive more data than what you can transmit, then you can make this, you can use multiple slots for receive, and you can use only one slot for transmit. That's also possible. Okay? There is a flexibility in TDD where the number of slots for transmission and number of slots for reception can be changed, can be scheduled. You actually request that, and scheduler or the other part can allow you to do that. Okay, that's possible. Here in FDD also, right? Sometimes this is receive frequency, and this is the transmission. Sometimes from the user's perspective, you may want to have a large bandwidth for downlink or receive, and you have only small narrow band for uplink, right? This is an asymmetric case. That's also possible in this case because you have a large bandwidth, you can have a small bandwidth, no problem. Okay. This is the case of FDMA/FDD. Each user uses two different frequency band for downlink and uplink, and all the users are separated by frequency. So this is FDD/FDMA/FDD. This example shows you the TDMA/FDD. Each user uses two different frequencies for uplink and downlink, but users are separated by time. Okay, time slot. So as I said, whether user 1 use this time slot and user 2 use time slot, that depends on the scheduler. Okay, what happens is that each user, whenever you wants to transmit, then you request to the scheduler, because we are talking about the multiple user scenario, right? We have multiple users, So there is a scheduler inside the base station. And typically, what happens is if the base station has some data to transmit to user 1, say, right? That's downlink. Base station has some data to transmit. Not the base station exactly, maybe user 1's friend, somebody else, right? Have something to transmit to user 1 so that eventually it comes to the user 1's base station. Okay? So think about the link between the base station and user 1 and all the users. Base station has data to transmit to the user 1, which means downlink. In that case, base station knows that how big data is. Maybe it has a large amount of data to transmit to user 1. In that case, base station, since the scheduler is inside the base station can allocate 2 or 3 or more time slots, okay? More as necessary to transmit such amount of data. However, for uplink, okay, the base station has no idea how much you have transmit, right? How much of data you transmit. So let's say user 1 have some data to transmit, okay? Then user 1 has to request to the base station and saying that I have this amount of data transmit, please give me some time slots. Okay? And then base station receives that, and base station will receive such a request from all these users, right? Not just user 1, but all these users. And base station runs a scheduler based on who has the priority, who has more data transmit, who has a good channel quality, and considering all these things. And then decide, okay, I'll give user 1 2 time slots. User 1, maybe you need only 1. Even though you requested 2 time slots, maybe I can give you only 1 because there are more users, more priority users out there. Okay, so I have only 1 left for you. Something like this. That kind of decision will be made by the scheduler inside the base station. Okay, so whether user 1 is here or there, or whether how many time slots user 1 use, that all depends on the scheduler. Okay, this picture just show you an example. Okay, but these amount of time slots, number of time slots can be flexible, right, based on the scheduler. But bandwidth cannot be flexible, right? Bandwidth has to be fixed. Okay, you cannot suddenly increase the bandwidth for user 1 and reduce the bandwidth for user 2. Okay, that's not simply possible. You fix the bandwidth like a 5 megahertz. Okay, fixed. Okay, and uplink also for a certain bandwidth it's fixed. Okay, you can play with the number of time slots, how many data you transmit. Typically, the FDMA, TDMA are combined. Okay, this picture shows you that there are 7 different users, 9 different users. 1, 2, 3 use the channel 1, 4, 5, 6 channel 2, 7, 8, 9 channel 3. Okay, so each channel you see that this is like a TDMA, but we actually have 3 different channels, so it is also a FDMA. Okay, so from the carrier's perspective, okay, we hear SK Telecom or Korea Telecom, those guys, those are carriers, right? Those are system operator. So from the system operator perspective, they own some frequency band, this amount of band, right? And they divide this whole band by the several channels, and of course they assign each channel to a certain area, okay, or certain purpose. Okay, so for each user, you are using only 1 band. Maybe you are in here or here. You're using only 1, but from carrier perspective, they have all these things. So this is how they operate, typically. Okay, this example shows you the concept of CDMA, right? Typically, in CDMA, the original signal is a narrowband signal. Narrowband means that our bandwidth is pretty narrow, which means that your symbol duration is pretty large. In other words, low data rate, generally. Okay. user 2, same thing. But this low data rate or large symbol duration is now multiplied with fast rate chip. Okay, this is called the chip rate. This is maybe symbol rate or bit rate. Typically, chip rate is much faster. So once you multiply your code into each bit, then this information is now converted into this rate, this one, right? And from the channel, this is channel. From the channel perspective, now your duration of this is chip duration. This chip duration decide your bandwidth, and now you multiply this fast chip rate. Your bandwidth is now spreaded. Okay, this is why we call it a spread spectrum. So this is what the bandwidth, the spectrum looks like for user 1's signal after you multiply your code. Same way for user 2, this was original narrow band, but once you multiply your code, since the code is based on the chip rate, fast chip rate, signal is spreaded. So therefore, this is the spectrum for user 2's signal. And when you transmit this thing, and when the user 1 also transmit these things, these two are now combined over the channel, and this is what is received by the base station. This whole thing is what's done in base station, right? Base station receives this signal, which is mixed of these two, and then the multiply user 1's code and multiply user 2's code independently, right? This is received code, and that goes to both way, okay? Each of that is called the channel card. In the base station, you have a multiple channel card, and each channel card typically do these things, okay? And user code, each user's code is already known by both, okay? The base station knows the user code, so you multiply that in order to recover the original data after doing low pass filter. And same way with this received signal, you multiply the second user's code, right? And then pass through the low pass filter, you recover the original signal of your second user, okay? Although you have multiple users, not just two, but multiple users, same thing happens. But in order to guarantee that the original data is recovered with no problem, what you have to make sure is that the code, right? Each user's code, the user 1's code and user 2's code has to be orthogonal, okay? Otherwise, this code and this code looks very similar, therefore you cannot really distinguish. So in order to make this guy and this guy to be distinguished, the best solution is to make this guy and this guy to be orthogonal. But orthogonal in this case, right, think about this one and this one. This code and this code is orthogonal because you multiply this 4 with this 4, right? Let's take the inner product. The first one times this first one, right? And the second chip multiply with this second chip, okay? Multiply 1 by 1, you add it all together. Then this product makes 1. The second product minus 1, 1 minus 1, or minus 1, 1, okay? So when you add it all together, it's going to be 0. That means it's orthogonal, okay? So that's how you have to design your code. However, in reality, what is actually happening is that ideally speaking, right, you multiply this code in the user 1, multiply user 2 in this one, and they are combined this way, which basically means that these two signals are still exactly synchronized. That's actually what I'm assuming in this picture. This one right here, this is what is transmitted by user 1. This is what is transmitted by user 2, right? I'm basically assuming in this picture that this chip and this chip are exactly aligned, exactly added together because this one and this one is exactly synchronized, okay? Time synchronized. That way you added these two becomes 2. The third one added becomes 0, right? Those are exactly aligned. That's what I'm assuming. If that is true, exactly aligned basically means that it's time synchronized from the base station perspective because this is what you receive by base station, okay? So time synchronization, that's our assumption here. Those are synchronized from the receiver perspective. So that's what you have to make sure. Remember that we talked about a time synchronization last week? Okay? It doesn't matter where you are. Maybe this user is close by. This user is very far away from base station. Even then, when you transmit some packet, and this guy transmits some packet, those two packets should be received by the base station at the same time with the synchronized fashion. So if this guy is close by, maybe you can transmit a little bit earlier, considering your path loss, because this guy is close, path loss is small, right? So you can transmit a little bit earlier. But this guy is far away, so considering path loss again, this guy has to transmit much earlier. That way, this guy's packet go through the propagation delay, not the propagation loss, propagation delay, right? This guy has a large propagation delay. This one has a small propagation delay, right? So considering two different environment, two different propagation delays, both one should be received by the same time, okay, at the base station. What if these two are not received by same time in the base station? Okay, what if these two are not synchronized from the base station perspective? Then what happens is there are two different ways of synchronous here. One is that maybe you are way off. That way, maybe third one is added to the first one. In that case, the difference, the delay difference between those two is like two chips. It's a huge delay difference. That's one case, which is really not that practical, because of course that should not happen. Okay, but what is likely in the scenario, in the actual scenario, is that we try to make a synchronization, of course, right? We always try to make them synchronized. But what is actually happening in reality is that because of some unexpected environment, right? There is always a fading, some of the multipath, some of the delay. What is likely is that this bit partially overlapped with the partially asynchronous with the other one. Okay, their symbol, this boundary does not match exactly with the symbol boundary. Maybe a little bit off by the symbol boundary. So in that case, the offset is less than one chip, but still there's offset. You know what I'm saying? It's not exactly, the symbol boundary are not exactly synchronized. That's a perfect synchronization, but that's very unlikely. What is likely is that it's a little bit off. But this offset, when these two time is off, that offset is less than one chip because of all this unexpected delay and multipath. So that's what is likely happening, which may or may not cause a problem. And that offset, let's say, is a little bit big. If that is very small, compared to your chip, if the offset is very little, then what's happening is that you are going to do a sampling anyway in some point, so that may not cause a problem. However, offset is a little bit bigger than that, still less than one chip, but it's a little bit big. Then what is likely happening is that your orthogonality does not 100% guaranteed. If your orthogonality is not guaranteed, what does that mean? Let's say this code and this code is not perfectly orthogonal because you have little off in the synchronization. What does that mean? That's like a little bit asynchronous scenario in CDMA. If that happens, that basically means that in this case, right, remember that simple mathematics we talked earlier? Let's say this is A1 and A2. Okay, A1 and A2, original signal. This is a code, C1 and C2, right? A1 times C1, A2 times C2, those are added here. So this signal is A1 C1 plus A2 C2. You multiply C1, so therefore, once you do that, A1 C1 square plus A2 C1 times C2. Now, if the orthogonal is not guaranteed, C1 times C2 does not go to 0. Okay? C1 and C1 times C2 will be small, of course small, but it's not 0. It's like something, 0.00 something like this, right? That is some of the leftover interference. Okay? Some interference remain if there's a offset. If that's the case, maybe it's okay because that's very small. Maybe it's okay if you think about 2 users. But now think about the base station. We have in CDMA cellular system, right? We are thinking about a 40, 50, 60 different users, right? And each user pair now cause this kind of interference, and that kind of small remaining interference will now being added, right? Okay, so eventually, if each one of them is asynchronous, such kind of small interference is now added on top of that, so that interference amount is not is significant. You cannot ignore that anymore, so that will block your transmission. That will reduce your capacity. Okay, so that is one of the fundamental facts of the CDMA. Now, if you look at the research paper, there are a lot of research papers. They talk about, describe, and try to solve this kind of problem. What if the time synchronization is not perfect? Okay, that is actually what's happening in reality. The synchronization may not be perfect in reality. Okay, this is only the ideal scenario. Okay, so such remaining small interference will, of course, impact the whole capacity, the whole operation of the system. Okay, that's one thing. The second thing, in CDMA, there's another thing we have to talk about. What is the important thing in CDMA? In order for yeah, power control. Power control is another big thing in CDMA. Why is that? I mean, why is there suddenly there's an issue? Earlier in FDMA, TDMA, that was maybe an issue, but it was not as big like this, right? So all these users use the same frequency, same time. Yeah. Now let's think about the scenario again. Let's say this guy is nearby, and this guy is very far away, right? And let's say let's not do power control. Okay, it's an extreme case. In that case, let's say this guy used the transmit power P. This guy also used the transmit power P. Since we are not doing power control, let's say we use the fixed power. Okay, P here and P here. In that case, this guy is close by, so this guy transmit by power P. That probably is received pretty strong by the base station because this is close by. But this guy is very far away, right? So even though this guy uses power P, when this power is delivered to the base station receives very small data, small power, right? What's the problem of that? I mean, same thing probably happened in the FDMA case, earlier cellular system, right? But in earlier cellular systems, for example, FDMA, TDMA, this guy is close by, user 2 is far away, and they use the same transmit power. User 1's power is received by this amount. User 2's power is received by small. That's okay, general, because they are separate by frequency anyway. Okay, each frequency is independent. Okay, so as long as you have a right filter, you should have a bandpass filter. Okay, as long as you have a right filter, it's not a big problem. TDMA. Let's say user 1 uses this time slot, user 2 uses another time slot. User 1's transmit power is received strong. A little bit later in time, user 2 signal has the small receive power. No problem, because that's a separate time, right? No problem. Here, however, these two signals are combined. That's what you receive. Now the user 1's power is this big. User 2's power is very tiny. That basically means we experience near-far problem, right? What is the near-far problem? I'm here, I'm talking to two different guys. One guy is nearby and another guy is far away. They talk to me with the same tone. I definitely cannot hear the other guy far away, right? Okay? In order for me to understand, this guy have to turn down his voice, right? This guy has to whisper to me. That guy has to shout. That way, these two guys' voice is received to me as the same power as possible. That's a fundamental, that's the most important thing for CDMA to operate correctly, okay? So it doesn't matter whether this guy is close by or this guy is very far away. It doesn't matter. For the base station, this base station wants to receive this power at the same level, okay? If that's a different level, we now experience some near-far problem. Maybe a little bit off is okay, but this is so big, this power is so low, then this user 2 is completely shadowed, right? So that's the problem. So that's why power control is so big concern and so big in CDMA. However, what is even more challenging is that we are talking about fading channel, right? Fading channel. So therefore, this guy transmits certain power. That power now experiences a fading. So that power is not actually consistent. Sometimes this guy's power is received by big, sometimes small, okay, because of fading. Same thing for user 2. So therefore, you have to actually change your power, transmit power, based on the fading and considering fading, all these things, okay? So in order to find out how much power this guy has to transmit, what this guy has to know is the distance. Okay? This guy at least has to know I'm close by. That way I can reduce the power. Or this guy has to know that, okay, I'm very far away from base station, therefore I have to increase my transmit power. So this guy has to have that idea. But how does this guy know that? How does the user knows that where's the base station? How close I am, how far I am. How do they know? They don't know, right? So that's why this guy receive, in this case, base station, has to tell each of them, okay, it looks like you are close by, okay? It looks like you are far away, okay? This guy has to tell them. That's one of the system parameter, okay? That way, this guy understand that, okay, I seems to be close by, so I have to reduce my transmit power. But even that transmit power is not accurate because we are talking about fading channel, right? This guy decide its own transmit power based on the distance, estimated distance, but that power is not accurate still. So therefore, even though this guy reduced its own power, base station may not receive the expected power. Maybe even in that case, base station receives higher than expected power or lower than expected power because of unexpected random fading. So therefore, this base station has to keep talking to the user 1. Okay, this time your power was a little bit higher than my expectation or a little bit lower than expectation. So this guy has to keep talking. Feedback. So what I'm talking about here is that we typically have two different power control schemes, right? Generally, open loop, closed loop. Okay? What is open loop power control? Generally, open loop power control. What was the open loop? We briefly talked about open loop earlier, right? Especially for MIMO. Open loop means just one way. Let's say open loop. Closed loop is like a closed loop. So in this case, in terms of power control, open loop basically means that this guy decides, based on the distance, this guy just decides how much power it has to transmit. Okay? So that's the open loop. Okay? No power control means this guy just fixed the power. That's the no power control. But open loop power control is that this guy understands the distance and then this guy decides its own transmit power based on this distance. That's the open loop. But that open loop power of course, is not accurate. So therefore, once this guy decides its own transmit power based on the open loop, and then transmits, but this guy is not happy about that power, so this guy later feedback. That's closed loop. Feed it back, saying that, okay, your power is a little bit higher than my expectation. Please lower a little bit. Okay, then this guy do a fine tuning. That's a closed loop. Okay, so always you have a open loop power control and the closed loop power control at the same time. Okay, first open loop and then later the closed loop. Okay, you always have two of them at the same time. Especially CDMA, that's a very important thing. In order for this, without this power control, such kind of power control, this system never works. Okay, very critical. And even the OFDM system, they have the closed loop and open loop power control. Okay, same concept is still there. Okay.
One question.
Yeah.
Offset and time synchronization. As you said, that it's likely that the offset is not more than 2 chips. So is it from the experiment, or do we have any other provision to ensure this?
Okay, good question. What is actually happening is that I'm just showing some scenario where this system is operating in a steady state. But initially, let's say this guy powers up. Let's say this guy suddenly appears, okay? And let's power up the user one, okay? Suddenly this guy wakes up, and what's the first thing to do? When you wake up, what is the first thing to do? You have to do cell search, okay? This guy absolutely no idea where I am, okay? So this guy has to search it. Has to search what? Search the base station. Okay, what base station is my base station? Like that, right? Has to search it. And when you search the base station, what that means is that you are doing synchronization. Okay? There is a certain synchronization process, time synchronization process. By going through that process, somehow your symbol boundary, symbol duration and symbol boundary is synchronized. Okay? So ideally speaking, okay, when you wake up, you anyway have to do the synchronization process. So therefore, ideally, your the chip boundary is exactly synchronized with the base station's the boundary. Same thing for others, right? So this guy synchronized its own time with the base station. This guy also synchronized its own time with that base station. So everyone does that. So therefore, I'm not talking about this boundary and this boundary same in here. Okay? You see what I'm saying, right? Remember that I showed you the picture and I said that only God knows the time, exact time. Remember that? This exact time, we have the timer, only known by God. Okay? In that case, this time definitely is different from this time, because this guy may be close and this guy may be far away. And this time, actual time, is based on your distance, right? Because this guy will transmit a little bit earlier than the base station's timer. And this guy, since this guy is far away, this guy has to transmit much earlier than the base station's time. What we are trying to do, what we are trying to do for each user is that when I transmit a packet, that packet has to be received by the exact base station's time. That's what we are trying to do, right? That way we are talking about synchronization. Okay? So that's why they have to do synchronization when they wake up. So each one does wake up and each one does a synchronization. So ideally speaking, when they transmit and each guy transmit, these packets should be received exactly synchronized fashion. Okay? So certain synchronization is already there by the process. Okay? So since we are doing such kind of synchronization, it is very unlikely that you are, way off. Okay? Because your chip is already synchronized by the process. However, small offset can be happening because of the fading, because of this the delay multipath. Okay? That's what I'm saying. Okay. We also learned about the SDMA. We didn't talk about details about this SDMA. We are just briefly looked at the concept of SDMA. This SDMA is space division multiple access, right? As you see here, each user is now divided by space. That's pretty interesting concept. This guy is here and another guy is another area. So therefore, if a base station can distinguish where and which direction each user is, then base station can divide the space. Okay, once you do that, now what is nice about these things is that this user is there, so this base station, if this base station has something to transmit to him, then this base station can focus all of the energy to him and only transmit to him because that's his data, which means that this transmission has absolutely no interference to others, ideally speaking. Okay, ideally speaking, that's what's happening. And this guy has something to transmit. This is actually for downlink. This base station has something to transmit to this guy. Again, focus only the energy to him. Okay, so that is actually intention. Okay, that's a very nice thing to do it if you can. And if you search the Google using the keyword smart antenna, okay, you probably see some articles like 10 years ago, 15 years ago. And initially, like 15 years ago, the concept of smart antenna appears, and they have similar concept like this. Okay. Now then, how can you achieve this? How is it possible that you can focus all of your energy to only this direction, or only to this direction? How is that possible? You may have a directive antenna. However, in that case, let's say you have a horn antenna. Okay, that's for transmission. Suppose that's the case. Then what is happening here is then now let's say you have to transmit to this guy. Then you have to focus your horn to that, right? Suddenly you have something to transmit to the other guy here. Then you have to turn your horn mechanically. That's very bad, right? No one do that. Even the mechanical thing is not as fast as your transmission, okay? So even in radar, right? In military radar technology, they always radar. What is a radar? You basically sweeping, right? Old fashioned radar, the actual radar antenna is sweeping, like it's a mechanically they steering like this, right? They rotating the beam mechanically. But these days, no one do that, right? They actually make the radar station, and they never move. Mechanical, not mechanically, but electronically, by feeding their the current, okay? They actually make a beam. We cannot see it, but they actually steering the beam electronically. That's what they do. Same way here, no one do mechanical steering. Okay, so it's a horn antenna is not a liable option. Another thing is that in order to do that, right, we can use multiple antennas, MIMO. Okay, we have multiple antennas. When you use multiple antennas, you can actually feed the current for each of these antennas. Especially, you actually can change or control the phase of each of the current for each of the antenna. Then you can actually make the beam like this. Okay. Simply, we call this one as a beam forming, right? Beam forming. So there are a couple of ways to do it. However, in reality, this is an ideal case. In reality, what's happening is that when you do a beam forming to here, okay, then main beam is like this into this direction. This is the direction that you want. Of course, you have a main beam here, but you always have some side lobes. Okay, side lobes. This is the main lobe, and side lobe is small, but still you have a side lobes in some unintended directions. So that side lobe will interfere some other users in some other places, right? So now in this area, one of the research that people are doing is that how you can reduce the interference, or how you can let's say some other users here, and you definitely will have some interference to this guy because of the side lobe. How can you reduce the side lobe, which is interference? At the same time, you want to maximize all the energy into the main lobe. Okay, that's the part of that. That's part of the research. Okay, but this area still is a little bit open. As I said, maybe 10 years ago, people were looking at these things, but it's still it's not being popular still. One of the reasons is that in this case, right, in order to focus your beam, first thing to do is that you have to keep track this guy. This guy is not static, right? It's mobile. They move around. So you have to keep track. That's not easy, right? This guy, let's say this guy is in train. You have to keep, tracking that. Okay, that's another thing. And as I said, that there's a still interference and things like that. So this is not easy. So that's why not that popular still, but that's still ongoing. We also talked about some random access schemes. By the way, why we are talking about random access? This is about random access. Earlier pictures, right? This one, and this one, and this one, these are all not random access. Okay, this is the access by multiple users, but these are somehow synchronized access. Suppose this one, right? User 1 and user 2, they use 2 different times. So therefore, user 1 should know that, okay, this is my time slot. User 2 should know that, okay, this is my time slot. Now suppose that these two guys are not synchronized. In that case, they don't know when to start. They don't know when to start, right? Even though they know it, maybe since they are not agreed upon on the timer, then it cannot work, right? So these pictures are, under the assumption of synchronization, perfect synchronization. Okay? Same thing here. But this picture basically talk about some random access. Okay? Random access basically means that we have no synchronization. That's random access. So why do we talk about these two different scenarios? This is random access, the earlier is not random access. Think about this case. Let me give you some simple example. Let's say I want to use this kind of system, uplink and downlink, okay? FDD system. When you think about FDD system, transmit from the user perspective, transmit and receive use 2 different frequencies. Therefore, you have to do the synchronization for each of them, okay? Remember that the picture that I show you. For uplink, since you are transmitting to the base station, your transmission should be a little bit earlier than base station time, right? Right? Because that way, your packet goes through the delay, propagation delay, and is received by the base station time. However, in downlink, base station transmits, okay? So after a little bit of propagation delay, you receive it, okay? So from the base station time, my downlink time is actually a little bit later than the base station time. My uplink time is a little bit before, a little bit ahead of the base station time, right? Of course, right? Now then, so which means that you have to do the synchronization of downlink and synchronization of uplink independently. So now, let's say you wake up a device. Okay, a device is now wake up out of nowhere. First thing to do is that you have to do the cell search. When you do the cell search, what you try to do is to get the downlink synchronization. Okay, you always have to first to do the downlink synchronization. In other words, you want to make your downlink timer to be synchronized with the base station time. Okay, that's first thing to do. So now let's say you did that. You did the time synchronization of downlink. Now your downlink time is synchronized with the base station. Then what you can do after that is now you can receive base station's message, because your downlink time, base station time is now synchronized. So whatever the base station transmit, now you can understand, because we are synchronized in downlink, right? So now you can receive some signals message. There's some broadcast message or system message. That system message has very important information, like what is my base station number, and what is the system parameter of this system, whether I'm in SK Telecom or KT, you know, all this information is inside the system message. So now you can understand system message, okay? But that's a downlink only. Then how can you make uplink synchronization? That's the question. For uplink, right, you have to transmit. That's uplink, right? But in order to transmit, your time, and let's say you transmit and base station receives this, right? In order to make that happen, your time and base station time has to be synchronized. That way you transmit and base station understands, right? But what we are trying to do is uplink synchronization. So how can you do that? Without uplink synchronization, you have to transmit something. Okay, how does uplink synchronization work? In downlink synchronization, how things work is that base station just transmits synchronization packet all the time. Because from the base station never knows that when each user wakes up. Okay, each user wakes up at random time. Okay, so base station has no idea when to wake up, when the users wake up, right? So base station just transmit the synchronization message all the time. That way, each user wakes up at random time. Each user will receive this synchronization packet at a certain point, right? Because I keep transmitting. So therefore, just try to match the synchronization of downlink time. But in uplink, users just wake up and that user try to make an uplink synchronization. How can they do it? They cannot do it, right? Simply. So therefore, you use a random access. Okay? Each user has no idea about uplink timing. Okay? So user now transmit some message in random. Okay? Do you understand what I'm saying? Okay, let me draw the timeline that we talked about last week. Let's say this is a base station timing. Okay? This is a timing of base station. And let's say we have a user 1. You have a user 2. In downlink, for base station, uplink timing and downlink timing are exactly same. Okay? Because this is the reference. Always the base station timing is reference. So they never changed its time. And uplink, downlink are exactly same time. However, from the user, if first thing to do is the downlink synchronization, but the base station transmits some packet like this, but the user 1 is close by, so the propagation delay is small. So user 1 will receive this synchronization packet a little bit later, like this. And this much is propagation loss, right? And once you get this synchronization packet, now the user 1 understands this synchronization packet and try to make this downlink timing to be synchronized with this, okay? So now the downlink, user 1's downlink timing is like this. This is the user 1's downlink time. And let's say user 2 is far away, so it has a more propagation delay. This synchronization packet is received by user 2 at this time. Okay? So this is the user 2's timing, downlink timing. So here, this user 1's downlink timing, user 2 downlink timing is different. Okay? So this can be easily done. User 1 or user 2 wakes up at random time, still the base station transmits the synchronization packet always. So therefore, let's say user 1 wakes up at random time, still it waits a little bit, it'll receive the next synchronization packet at some point, right? So therefore, it can synchronize itself. Same thing for user 2. So downlink timing is not a big problem. Now the thing is that the uplink, user 1 and user 2, they don't know about the delay. Okay? User 1 has no idea about how much delay it has. Okay? And also the base station doesn't know. No one knows. Okay? No one knows what is the delay. So therefore, user 1, in order to make a synchronization, user 1 has no knowledge about the uplink timing. So therefore, user 1 just transmit packet randomly. Like this. User 2 also. User 2 just transmit this packet in random. It can be random only because you have no synchronization for uplink. That's what we are trying to do. So user 1 just transmit random packet, but it happened that user 1 is close by, so therefore this is the propagation loss. So when you transmit this one, which is a random packet, it is received by the base station at this time with a little bit of delay, the same delay of this one. And this guy's random access packet is received by user 2, received by base station with this much of delay because the user 2 is far away, so this much is the propagation delay. So therefore, user 2's random access packet is received by base station at this time. Okay? Now then base station find out, oh, looks like this is user 1. The packet has a ID. So this is a user 1, this is a user 2. Looks like a user 1, you are this much far away from my time. This is uplink time for base station. User 2, looks like you have this much time offset. Okay? Now the base station knows it. And then base station now knows this much of delay. And how much is this delay? What is this delay? This delay is actually round trip delay. Okay, this is round trip. Okay, because base station originally transmitted certain data. That data experienced some propagation delay and then received by user 1. And now it's synchronized. And based on this synchronization, you transmit the random packet. That packet is again experiencing another propagation delay over uplink that is received by base station. So this delay is round trip delay. So once the base station knows the round trip delay, the base station can tell the user 1, okay, looks like your round trip delay is this much. Okay, which means that half of the round trip delay is your propagation delay. Same thing for user 2. Now the user 2, the base station, now the base station has to tell this much of delay to the user 1. So base station send a message to the user 1. Okay? This is your propagation delay. And also send a message to user 2. This much is your propagation delay. Based on that information, now the user 1 make its own synchronization, uplink synchronization. This is a user 1 uplink timing. This is user 2 uplink timing. Right? User 1 has to transmit this much earlier. User 2 has to transmit this much earlier in order to meet your packet is received by this time. Okay? So that's how the uplink synchronization works. First thing is that you have to transmit random access. Downlink synchronization is always easy, okay? Because the base station always transmit the synchronization packet, okay? But uplink, it's not the case. So first thing to do is you have to do random access, and then based on this round trip time, user 2 will synchronize uplink timing. So this is where the random access is used. Okay? So for every system, you have a random access part. You also have a synchronization part. Eventually, what we want is that we want to make uplink timing and downlink timing to be synchronized. We definitely want to make a synchronous system. But in order to make a synchronization, we often go through the random access procedure. Okay? That's one of the reasons where one of the application you look at the random access. Okay? First example of random access. Probably the most common example. Another example for random access is this one. Now think about your internet access. In here you have a computer, right? You can you can search the internet. Let's say you go to the Internet Explorer and search the web, okay, in the browser. Once you do that, then internally they have a TCP/IP protocol, and they make an internet packet. That packet now goes through the internet, right? Goes through the channel, wired channel. That access is not synchronized. So that is random access, right? There's no synchronization thing. You have just cable. Whenever you transmit, whenever you have a packet to transmit, they just transmit with no agreement on time, no synchronization. Whenever you need, you just transmit. Okay? That's random access. Sometimes in that kind of scenario, random access is efficient because making synchronization is a lot of work, right? Think about that. In order to make the synchronization, you actually have to go through a lot of process. So it's in cellular system, we need to do this. However, in wired, just whatever you need, you just transmit, random access. That's more efficient. In that case, however, what's happening is I have two computers here, and accidentally, two guys try to send a packet at the same time. Then, since there's no synchronization, they will collide, right? That's what we are trying to talk about here. That's the scenario. So let's say that you have 3 different users, maybe 3 different computers, and these 3 computers try to access the channel, internet, or the channel, LAN, okay? LAN channel at random time, okay? User 1 suddenly make a packet to transmit. User 2 suddenly, at random time, transmit a packet, and it just happened that they collide. Once this is collide, these packets are merged, right? Then it's collision, and this becomes garbage. That's the problem of random access, generally. Okay, so this second slotted aloha, what they try to do is that in order to reduce such collision, they are introducing a little bit of synchronous concept, but this is not exactly synchronous. Still, it's random access. But earlier, it's a pure random access, but this one is a random access based on the slot. So you can only transmit when the slot starts. But which slot you choose, that's random. Okay, still random. But in this case, still there's a collision. So therefore, this CSMA concept appear later, which means a carrier sense, right? When you try to send a packet in random, you first sense if the channel is busy or not. If the channel is busy, which means that someone else is using it already, then hold it, okay? If no one is using it, looks like a channel is empty, then you can transmit. That's the CSMA, right? So right here in this example, user 1 was using the channel, and user 2 sense it, right? And then user 2 look at that this is busy, so therefore it hold it and do a back off, and then it transmit later. Even then, you may have a collision because maybe the user 1 was transmitting, and user 2 and 3, these 2 guys were waiting, maybe, right? And these 2 guys are sensing the channel, and these 2 guys hold it. So therefore, these 2 guys may start to transmit at the same time. So still there's a possibility of collision. So therefore, in CSMA CD, you have an additional feature called the collision detection, which means that when you transmit, you also listen. your transmission. So therefore, you transmit and you listen at the same time. And it looks like when you listen it, you are listening only your packet. That means you are the only one in the channel. So you are free to go. But when you transmit and while you transmit, you listen, but you are listening garbage. That means someone else is also transmitting. In that case, whatever you transmit, that's going to be garbage anyway. So just stop. As soon as you detect such a garbage, you stop. That's collision detection. Okay, so that's the how to do. Okay, there was so much time of review last week, but this is today's lecture. What we are going to talk about today is some basic of OFDM and single carrier FDM. Okay, so just to help you understand, let's start from a basic. Okay, basic here is a single carrier system. Okay, let's think about single carrier baseband system. We have a single carrier system here. We have something to transmit, ST, okay, in the transmitter. Typically in the transmitter, this part is transmitter. In transmitter, when you transmit, you have a transmit filter, okay, for a couple of reasons. You have some transmitter, let's call it a G sub T, that's a transmitter filter. This is what you transmit. You have a channel, okay, and in the channel, after channel, fading channel, you have AWGN, noise is added. At the receiver, this part is receiver. First thing to do is a receive filter, okay. After that, you have an equalizer, and then you do a decision. What we can do is that we can make a model like this, and we can combine these three blocks, okay, pull together, and let's call that a PT. Okay? And PT is something like a virtual channel. This is actual channel, but considering the transmit filter and receive filter, put them all together and make this whole thing as an effective channel. Okay? We can consider it that way. Once you do that, now as you can see here in the mathematics, y tilde t, this one, okay, y tilde t, this one is a convolution of all these things, all this, right? S of t is convoluted with gt, which is convoluted again with ht and grt. Okay, so you have 4 different convolution because we make each one as a block. That plus you have noise here, and that noise also goes through the filter. So therefore, noise convoluted with the receive filter. Okay, that's what you receive here, y tilde. Okay, and if we combine this and put that as a p of t, then we can simply simplify this one as a s of t convoluted with the pt, and z0 t. That's a here, as you see, a band limited noise. What does that mean, band limited noise? We didn't say anything about band here. Okay, we have only ZT. Here's ZT, but suddenly it says a band limited. What does that mean? Yeah, that's right. Then now the question is why is the band limited? How come it's band limited?
Because you have now receive filter, which is just receiving.
That's right.
Band.
What does the receive filter do?
Because
What is the receive filter?
I mean, not the all band, but only the band pass.
Yeah.
Band pass phenomenon.
Okay. Yeah, that's a good point. Now then, you see that why do we have a receive filter, right? Typically, this is a receiver. Okay, and receiver and also transmitter, they have operating frequency. This guy is not operating with any frequency, right? They already agreed upon a certain carrier frequency. So typically, you need the receive filter in order to filter out all the other frequencies. Okay, I want to look at only my frequency, carrier frequency. That's why typically you need the receive filter. Another one is that the transmit filter. Why do you need the transmit filter? Couple of reasons. One of the reasons is, again, make the right spectrum. All these things is about spectrum. Okay? This one, receive filter, is like a bandpass filter, which means that you are basically cut off. You are basically making your spectrum to be right here after the receive filter. You want to only look at your spectrum, your frequency band. Okay? But let's say you don't have receive filter. What happens is that you, in the spectrum, okay, there are a lot of wireless devices. Okay? Like you have Bluetooth, you have many others. Even in the Bluetooth, let's say, or wireless LAN, even 2.4 gigahertz, you are not the only device. There are many other devices which uses other bands as well, right? There are so many devices using so many different bands. You don't want to look at all those. What you want to do is that you want to look at only my band, my carrier frequency. So you have to manage the spectrum so that you want to remove all the others. I want to look at only my band. That's why you need it. Okay? Some of the spectrum management here and transmit filter. One of the reasons is that if you maybe this is a binary data or some of the symbols after modulation. If you just transmit this as it is, then you cannot make the right spectrum. Your spectrum may have a peak somewhere. Your spectrum may have a long tail. That's very bad, right? Your spectrum has to be limited with a certain bandwidth, because sometimes that's the regulation by the federal agency, the frequency, agency, right? And also, that's simply, you have to make it like that. You have to make it band limited, right? You are not allowed to transmit like a wide, right? So therefore, you have to make a sharp tail. You have to make some nice spectrum. You also have a certain spectrum about the out of band spectrum. What is out of band? This is your band, okay? And the outside of your band is out of band. There is always a specification where when you transmit, your out of band spectrum has to be lower than a certain power. Okay, that's the regulation. So you have to meet the regulation. Therefore, you need the transmit filter. But simply, that's the frequency domain perspective. Think about the time domain. Okay, frequency domain. What you need to do is you have to do the frequency, the spectrum shaping. Okay, you have to shape the spectrum so that you make a nice shape of spectrum. That's why you need this one. But in time domain, what do you call that? Spectrum shaping filter looks like a smoothing filter. Okay, you need to make your time domain sequence to be smooth using this filter. So this is like a filter, like a smoothing filter, like a low pass filter, generally. Okay. But the purpose of doing this filter is to make a spectrum shaping. Why the spectrum shaping? Because this whole block, like a P of T, right? This PT, transmit filter, receive filter, all these things is about the spectrum. Spectrum management is so important in single carrier. So that's what we do here in the single carrier system. So the receive filter is a band pass filter. Okay, we want to reject all the other the spectrum, the frequency band. I want to look at only my band. Therefore, your noise is also rejected from all the other band. Therefore, it's going to be band limited. This is what is likely in the single carrier baseband system. Let's say we have a channel looks like this. And this is our channel. Always you have a multipath in the channel, right? In time domain. This is time domain, impulse response of the channel. This is a frequency response of the channel. You do the Fourier transform of this, then you get the time domain frequency response of the channel. Okay, let's say this is frequency and this is time domain response of the channel. Now then, given this channel, what we are trying to transmit is that we want to transmit information 1, 1, minus 1. Let's say that's what we want to transmit. Okay? Ideally speaking, if the channel is perfect, then we can transmit 1, 1, minus 1 with any symbol duration because there's no multipath. But in this scenario, we have a multipath like this. What is happening is that when you transmit 1, 1, minus 1, now depending on the symbol duration, we have a different symptom. First thing, by the way, why do we have this shape? That's because of spectrum shaping filter. Okay, when you have a 1, 1, minus 1, now that's here. When you transmit, you have to go through the transmit filter, which is spectrum shaping. Therefore, it looks like this, something like that. Okay. Now then, you transmit this one, but our symbol duration is this much, which means that it's a narrow band system. Okay, low data rate system. You transmit packet once in a while. Okay, very low data rate. In that case, even though you have a multipath of this much, because of this red, green, gray multipath, you probably have these echoes. Okay, these are echoes. Still no problem, because each symbol is very far away. Even though you have echoes, you're gonna make a sampling here, somewhere here, somewhere here. It's not a problem. Okay, echoes will be ignored anyway. Okay, so no problem. This was the case of frequency fading, frequency flat fading channel, right? Remember that maybe second week we review all these things, right? This is the case of frequency flat. I'm not talking about the wireless channel, okay? I'm talking about general, okay? Even in the internet channel, right? Wired channel, this happens. This is a time domain. If you look at the same thing in the frequency domain, right? This is the frequency, the channel, frequency response of the channel, as we see here. And our information actually has a narrow band like this. This is our information. Since this one is a narrow band compared to frequency response of the channel, this narrow band signal, now we can consider that within this duration, the frequency narrow band, our channel is considered as a flat, right? That's why we call it as a frequency flat fading. Now let's think about the high data rate system. Our symbol duration is this short. In that case, this echoes is not really, it is a problem, right? You cannot ignore that. So we have red one, and you have a green and gray because of this multipath. Now as you see here that the gray from the first sample is being added with the second symbol. So once you sample it here, now then part of the first symbol, which is gray, and also part of the second symbol, red one, they combine together in time. Now you have an intersymbol interference, right? That's intersymbol interference. And this problem becomes worse when you have a large multipath or many more multipath. Because of this intersymbol interference, what you need to do is that you need an equalizer. And equalizer is nothing but just filter, like this. It is a filter. Okay? That's why you need this equalizer. Okay? You need a filter in order to remove that. So once you have an equalizer, ideally speaking, this equalizer will change this one into this one. Okay? Equalizer will grab the green one and the gray one, okay, and put them together in order to make perfect synchronized symbols like this. That's what the equalizer do, ideally speaking. But equalizer is just a filter, so therefore it's not as perfect as this. What is actually happening is that some of the interferences still remain. Okay, interference is still remain. It's not perfect. Okay, but anyway, that's the thing. And this is the frequency view of this one, right? Since we are talking about the short symbol duration, we are talking about the wideband of the signal. So therefore, within this signal duration, your channel actually has a lot of up and down, which means that it's a frequency selective channel. Now compared to this single carrier system, what we are trying to talk about is a multiple carrier system. Okay? Here's a simplified picture of a multiple carrier system. We have the same data to transmit, S of t. Okay? And this S of t is now divided into each of them. Okay? This one maybe is a series of bits or series of symbols. First symbol goes to this. Second symbol goes to this. Something like that. Okay? Or maybe you can use the same information. Doesn't matter actually. But this information goes to there. And you have some h of f, which is what? Transmit filter. Okay? You have a multiple n times transmit filter, independent transmit filter. Okay? And then you add it all together and transmit. We have a fading channel with noise. At the receiver, similarly, you have a receive filter like this. Okay? You combine together, you recover S hat. And GT here is a matched filter of H. So you use some filter, you use a matched filter in the receiver. Okay? This is a basic concept of multi-carrier system. And the reason that we split this one into H0 to HUN is because that if you look at the frequency domain like this, you know, frequency response of the channel is always not flat. It's like it has a fluctuation up and down. So therefore, we want to treat each of these frequency being differently, okay, like this. So let's look at a little bit more detail. Okay, a little bit detailed structure of a multiple carrier transmission. We have now different samples to transmit. Now you see that I use the capital X. What does that mean, capital X? Capital X means that I'm in the frequency domain. Okay, I'll talk about that in the next slide. But anyway, I have a different data to transmit. I have x0, x1, xm-1, so we have n different samples. Each of them can go through independent encoder and baseband filter. And this information is now multiplied by f0. It's modulated by f0. Okay? Each data is modulated with a different frequency. That's what it is. Okay? And then all of these things is now combined and then transmit over the fading channel. And at the receiver, this is reversed, right? Yeah, this is flipped. Okay, this is f0. Okay, I think I copied this one and flipped it, and these are flipped over. f0, f1, fn-1. You use the same frequency. Okay, you do a demodulation, and you go through the baseband filter to filter out all the other band, and then recover the original one. Okay. In the frequency domain, if you look at this one, then you have f0 here, f1 here, and now this f0, this process, encoder, filter, and this one, now looks like this one is a single carrier system, right? Each of them is a single carrier system. So what the multi-carrier system does is that you put the multiple single carrier system in parallel. Okay? Each of them is just single carrier system, and you just simply put them in parallel, simply speaking, right? Even in the frequency picture, as you see here, each one is just single carrier, but we just put them together like this. Let's look at the OFDM. OFDM basically follows the same concept. Here, we have n samples from the x0 to xn-1. Again, we have n samples. Capital X means the frequency domain, so we have n frequency domain samples. Each one now go to different modulation. Okay? You can use the same modulation, in fact, but you can use a different one if you like. You use each one independently go through the modulation. And then this 0th sample is modulated by f0. Second one, f1, x1 is modulated by frequency f1. Okay, each one now is being modulated with the different frequencies. That's actually same as the previous picture, right? We already talked about in the multi-carrier system that you have a multiple data in parallel. Each one is modulated with a different frequency. We already talked about it. What is different in OFDM compared to the previous picture is this relationship. You see that the previous picture here, let's go back here, multi-carrier. In this multi-carrier, I didn't talk about anything about F0, F1, Fn. You can use any frequencies as long as F0, F1 is separated enough. Like F0 is here, F1 is here. As long as you have separated frequency, you can use that, right? But if you separate F0 and F1 enough, that is like inefficient, right? Because we use wide spectrum anyway. So in OFDM, this is an important relationship. We choose these frequencies to satisfy this relationship. Fk equals to k, multiple of F0. F0 is like a basic unit frequency, and all the other frequencies are multiple of that. Okay? That's the relationship. Once you do that, like this is F0. This F1 equals to 2 times F0. Okay, and actually this should be k plus 1, right? Yeah, this should be k plus 1. Because in that case, F1 is the same as F0. So it should be k plus 1. So F1 here is a 2 times F0. Okay? F2 is a 3 times F0. Something like this. So once you do that, then you will see this kind of picture in the frequency domain. You have F0 here, F1 here, F2 here, like this, right? Since the frequency is a multiple of F0. Okay? All the other things are the same as the multi-carrier system in the previous slide. Okay? Each data is independently modulated by different frequencies. Okay? And at the receiver, you receive the whole thing and then demodulate each symbol. Okay? And now each symbol goes through an independent equalizer and demodulation. Because earlier here, we anyway independently use a modulation. So you independently do a demodulation. Now then, as you see here, even equalizer is independent. Why? Well, we use actually one channel, but even equalizer independent. Because this picture, and in here, let's say the fading channel, now we have this much of frequency response. This is the frequency response of the channel. And this is what we transmit. Okay? We make this kind of OFDM transmitter using these frequencies. Then you make this kind of spectrum. This is what you transmit. And this is what the channel looks like. Okay? This is transmission. This is what the channel. Now, you can see the next picture. I don't know why this all flipped. Now look at this picture. Then I'm basically making a virtual channel like this. Okay, this is not an actual one, virtual one. What this means is that when you look at this OFDM system, a little bit different perspective, what you can see is that this information is modulated by F0, okay? And they are actually all combined here and transmitted over the channel. However, each one is modulated by different frequencies. It is actually same to see that this information, the first sample now goes through this H10 channel. Okay? And that is received by this one. So this first path, which use the frequency of F0, this is completely independent. And the second path, this second one uses the second symbol, and that symbol is now modulated by F1. And that goes through another channel called H11, and then that is being demodulated and equalized like this. So this picture shows you that each of these frequency path is completely independent. In other words, we are talking about multiple single carrier system in parallel, completely independent in parallel, right? This one is independent completely. This is the frequency domain view of OFDM. Okay? And earlier in the previous in the previous picture, this is what you transmit. This is the channel. This is channel, right? This is what you transmit. So when you transmit this one, go through this channel, this is what you receive, right? Your transmission was the same transmission level, spectrum level, but we have a different frequency response of the channel. So therefore, F0 may have a good reception, but F2 actually has a very small reception, right? Because of the channel. So depending on the channel frequency response, you receive these things, right? Each subcarrier, each one is called the subcarrier. Each subcarrier is received by different power. So therefore, what you need is an equalizer. Okay? What this equalizer does is that this equalizer, the first equalizer, which is about the F0, that equalizer try to make this size, try to recover this size. Let's say this one, right? The second equalizer, which is about the F1 frequency, that equalizer try to recover this one. And the third equalizer try to recover this F2 subcarrier. So each subcarrier now try to recover each of the corresponding subcarrier. Therefore, after you go through the equalizer right here, you want to recover this one. You want to recover this one from this. Okay? This one now goes through the equalizer. Each equalizer recovered each of these subcarrier. Therefore, you recover this one. So simply, what the equalizer does, this is, by the way, we call this a frequency domain equalizer. Because we originally started from frequency domain. Okay? When you go through IFFT, now here we have a time domain samples. At the receiver, you have FFT, so we go back to the frequency domain, and equalizer is right there. Okay? That's why we call this a frequency domain equalizer. And using this frequency domain equalizer, now each equalizer is very simple. And what each equalizer does is simply recover this by multiplying one tap. Okay? Changing the size and rotating the phase. That's it. Simply speaking, you multiply one complex value. That's it. Okay? And depending on that magnitude of that complex value, depending on the phase of that magnitude value, you recover this one into this one. Okay? So therefore, each equalizer is just one tap equalizer, one complex value multiplication. So that's why we say that equalizer generally is very simple. That's one of the very fantastic feature of OFDM. Going back to the single carrier system, right? We need many taps in equalizer. Many taps. Okay? But even then, still you have a remaining interference. This is a fundamental reason why your telephone modem earlier cannot exceed 56 kilobps, right? Because of the remaining interference. Okay? That was a fundamental reason. Okay? And this is another reason. And this is also modulation. In this OFDM, you can use independent modulation for each frequency. And this one and this one, these two nice features are fundamental reason why now the ADSL technology, okay, is popular, not the telephone modem. No one uses a telephone modem these days, right? Okay? With the same wire, telephone wire, no one uses a telephone modem. Everyone uses ADSL. Okay? Why is that? Because the telephone modem, they use equalizer, very complex equalizer. Even then, you cannot exceed the 56 kilobps. With the same telephone wire, you use this technology, you can achieve several megabps. So that's why. Okay? So equalizer is very simple in OFDM. And you can use independent modulation. Why do you want to use a different modulation for each of them? That's because this one, right? This sample used the frequency F0. This is frequency F0. In this case, as you see here, the frequency response of the channel is pretty good. So therefore, you can use higher modulation. This case, it's a little bit worse. Maybe you can use a little bit lower modulation, right? Each of these frequency band is completely independent, as you see here, right? So therefore, you can use independent modulation. You can use independent equalizer. You have independent channel coefficient, okay? How is this possible? Just because that we use IFFT and FFT, and because of this IFFT, FFT, we have this relationship of the frequencies, carrier frequencies. You have a multiple of that. And then nice thing about this relationship is that once you choose a frequency this way, okay, you choose this frequency this way. Now as you see here, we have overlap between the subcarriers. But overlap of subcarriers is not a problem in this case, okay? Because that you basically, this block is we call as channelization, okay? Because actual channel looks like this, and this IFFT is the block you make this picture. So this channelization is done by IFFT, okay? And this block, FFT, is like a dechannelization. You recover this one, right? And then this FFT, IFFT, inherently, they actually make a process like you make each of these subcarrier frequency to be this frequency. And as long as you make a sampling at the right position, okay? F0, F1, okay? At the right position, as long as your sampling is at the right position, you can make actually perfect orthogonality. Okay? This is the picture why this is true. Think about that. Let's think about the example of 4 subcarriers. Okay? Let's simplify the scenario. We are talking about the 4 subcarriers. Let's say this is F0. Okay? And F1 is 2 times F0. Okay? As I said, this is a multiple of that. So 2 times. 2 times of 0. Therefore, you see that this is 2 times. Okay? Within 1 period of F0, you have a 2 period of F1. Okay? Same way, this is a 3 F0, 4 F0. You have a 3 period within 1 period of F0. You have a 4 period within 1 period. So these are multiple of that. Once you use these 4 frequencies, now in the frequency domain, you see that you have these overlapped the subcarriers, and these are orthogonal. How do we know these are orthogonal? Simply you multiply with this one with this one and add it, right? It's like a 1, 1, minus 1, minus 1, and you have a 1 minus 1, 1 minus 1. It's like this, right? You add it together, combine that, and you do addition, multiply and addition, then you will see 0. Okay? For this sine and cosine, if you like, then you can do integration of these two, or these two, or these two, any of these two. You see that each of these frequencies are orthogonal. Okay? So each of them is orthogonal. And fundamentally, what the OFDM does is that you basically combine these 4 frequencies with a different coefficient. You multiply some coefficient here, another coefficient here. So you combine these 4 frequencies in order to make your transmit signal. Okay. Now let's look at from the time domain perspective. This is a time domain view of the OFDM. Okay. So far we looked at the frequency domain view, and this is the time domain view. Initially in time domain, let's say you have some data to transmit. And originally, let's say you have a bits, TB. Okay? TB. Let me see. I don't know why this. You need n of them, so you need n bits. Okay? So originally, you have n bits, like this. These are n bits. And each bit duration is the TB. So therefore, this whole block has the duration of TO, Okay, TO is n times TB. Okay, and then each bit is now go to the independent path and is modulated by BPSK. All these BPSK modulated symbols now go to the IFFT, okay, and then they transmit like this. But once you do the IFFT, now you have a time domain samples. Earlier in here we are in the frequency domain and time domain samples. But what is maintained is that still your symbol duration is TO. Symbol means here is an OFDM symbol. The OFDM symbol duration here is still TO. Okay? But this is the time domain samples. Earlier we were in the frequency domain, but later we are in the time domain. But still we have TO. So what is happening actually is that original TB, the bit duration was TB, so tiny, but that tiny TB goes through the IFFT. The output is a collection of time domain samples which make a TO. But think about the IFFT procedure. What the IFFT does is that each output, time domain output, is a combination of all these inputs. Another output is again the different way of combination of all these things, right? Different way of weighted addition of all this. So therefore, if you think about the independent path of each of that, okay? Now let's think about that each path is independent. Okay, we are talking about the first path, second path, independent. Okay, in that case, this H1 0 and H2 0. Okay. This one, this channel, now becomes flat fading because this right here, your transmission symbol duration actually becomes a TO. You know the frequency flat and frequency selective. That's based on the relationship, right? Ratio between the symbol duration and the multipath, the delay, right? There's always relationship, right? So if the symbol duration is larger, much larger than delay, then it's a frequency flat. So once you divide this one into a multiple parallel path, then each parallel now become frequency flat. Okay? And each one is independent. This is flat, frequency flat, and each one is independent. So that's what is happening in the OFDM. So that's why people say that in OFDM, you are basically changing the frequency selective channel to the frequency flat. That's why they call it that way. Okay? So this picture is from the last week. Here, let's say you have, as I said, you have n T sub b series of bits, and you go through the serial to parallel converter. The first bit goes to here on the first subcarrier, second bit goes to the second carrier, and things like that. But now, when you do the serial to parallel, each bit duration is now increased into T sub b, n times T sub b. Okay? Earlier, the bit duration was TB, but now each bit has this bigger. So therefore, compared to this channel delay, now the symbol duration is much larger. So each of these paths, okay? Since each of these paths use a different frequency, it's independent. So each path is now frequency flat. Okay? So the parallel of frequency flat channels.
One question.
Yeah.
If it is frequency flat, we have learned that we don't need equalizer. If the channel is flat.
Okay. In frequency flat, exactly, exact word is that in frequency flat, you need one tap equalizer. We typically don't call that as equalizer because just multiplying one tap is nothing. Okay? We typically call the equalizer when you have multiple taps and when you do design of equalizer. But one tap is nothing to do design. Okay? One tap is just one multiplication. So some people simply say that, okay, we don't need the equalizer in frequency flat. Just one multiplication is nothing. But actually, you need, even multiplying one tap is actually equalizer. Very simple, probably the simplest equalizer. Okay? That's what you need in the frequency flat. You need to multiply one tab or one coefficient. You can call that as an equalizer.
But in fact, only amplifier maybe in the other case.
Not just amplifying, but you also need to rotate the phase. So you want to multiply one complex value. So someone may call that as an equalizer. Someone may not call that as an equalizer. Okay, this is the block diagram of transmitter and receiver for OFDM system. We have all this talked about all these things, right? And you see that this is one tab equalizer. Okay, and let's go to the next slide. So now, so far we talked about OFDM. Okay, earlier like OFDM, orthogonal frequency division multiplexing, OFDM. So OFDM is for one user, single user, right? Going back to this picture, this is a single user. Okay, you have a lot of things to transmit, and you want to use all these frequency subcarriers, right, to transmit many data in parallel. Okay, this is for one user. What is happening is that you can think about OFDM A. A means access, so it's a multiple access now. It's not OFDM, but it's not really. It's fundamentally the same. What is different here is that now you can think about multiple users. In this example, shows you the case of two users. Okay, you can now think about multiple users, and each user uses OFDM. Okay, so it's just an extension to a multiple user case. Each user will use OFDM. However, in this case, what happened is that in the earlier OFDM, since you have one user, you want to use all the frequency samples. Okay, you want to use all the frequency subcarriers. But in this case, user one still have the same OFDM. Hardware-wise, it's exactly the same OFDM, but user one wants to use only some subcarriers, like F0 in this example, F2, and some other subcarriers, and also Fn-1. Okay, and user 2, they also have the same hardware. User 2 wants to use F1, F3. Okay, so they only use partially. They do not use all the subcarriers, but they use partially. How many subcarrier you use and which subcarrier you use, who has to control that? Has to control by base station, right? Because each user is independent. Whenever we talk about multiple access, okay? Multiple access basically means that we have many users, right? That's why we call this multiple access. When you have a multiple access, since there are multiple users, you should have a central station called the base station, right? You have to have a base station. Always base station has a scheduler, okay? So which subcarrier you use, okay, and how many you use, that all depends on the base station. Base station controls everything like this. So base station tell user one, okay, you can use F0, F2, blah, blah, okay? And the base station also tells the user 2, you can use F2, F3, and blah, blah. Okay? In that case, what the user 1 does is that you make your own data to transmit and allocate some of the data to F0 and F2, okay, for those subcarrier you use. And for unused subcarrier like F1 and F3, these two subcarriers you should not use, right? For those subcarriers, you put 0. Okay, you put 0, 0 here. In user 2, you do it the other way. F1, F2, you load your data. You allocate the data. For unused subcarriers, F0, F2, you put 0. So that way, these two goes out to the air, over the air, right? These two will be combined, and these combined signal will be received by base station, and this is the combined picture. User 1 use the F0, F2. User 2 use F1, F3. They combined like this. Okay, that is received by the base station. And base station, what it does is that base station go through just a single FFT. Okay? In CDMA case, right? Remember that the base station receives the receives signal and it multiply the different code to recover the different user signal. But in this case, you don't have to do that. You just go through the one FFT, which recovers all these things. And now, since the scheduler knows that F0 is for the user 1, F1 is for user 2. Scheduler knows it, right? Because scheduler tell them that's the way to use it. So therefore, once you go through the FFT, now you recover something. Then based on that scheduler decision, now you know that the first one is the user 1's data. Second thing is the user 2's data. It knows that, right? So you recover all these things with the different users' data. Same thing happens for multiple users. Okay, even though you have multiple users, scheduler can assign which subcarrier and how many subcarrier they can use. Okay, and they are all merged at the channel which is received by the base station. Okay. Okay. So far we talked about OFDM and OFDM-A. OFDM-A and OFDM fundamentally is the same technology. And you look at we have good things about this and bad things. Generally, good thing about this is that it used the spectrum very, very efficiently. Why is that? Why do you say that OFDM used the spectrum very efficiently?
Because there are no blank spaces, a lot of subcarriers, and you can chop them more.
Compared to FDM, that's correct. But let's compare that with the single carrier system. Compare this multi-carrier with the single carrier. Then why do we say this is efficient? Tail, right? Yeah. So what happened is that when you talk about the single carrier system, right? Typically you have a long tail, large tail, like a band, right? But in OFDM, it is actually a collection of narrow band, and each narrow band has a very sharp tail, right? So therefore, the boundary actually is very sharp in OFDM. Compared to single carrier is like a slow, like this, right? But in OFDM, it's very sharp. So therefore, you actually can make more efficiently, spectrum more efficiently. And second reason, more important reason, is that each subcarrier now we can treat independently, right? That's what we mentioned. It is just simply a parallel of multiple subcarriers. Each subcarrier is independent. And each subcarrier, you can use a different modulation and treat differently depending on the channel response. So therefore, in single carrier, it's not possible, right? Single carrier, you just use it same thing. You just transmit same thing, same power, everything same. Although you have a fluctuation in the frequency response. But in this OFDM, you basically do it this way. So that is another fundamental reason why we say that this is much more spectrally efficient. Much more.
In this case, base station decided which kind of modulation user should use?
Uplink, yes.
Because
downlink, no.
No feedback. So base station should assign that you can use this modulation and this modulation.
This case, you should have a feedback. Because we are talking about adaptive modulation here, right? So depending on the channel condition, you may use the higher modulation, you may use a lower modulation. So only the receiver knows this channel condition, right? So you should have feedback. Yeah, you always have a feedback. For adaptive modulation, you definitely have to have a feedback. Okay, so So generally you should have feedback. That's somehow underlying assumption. Yeah. So the spectrum is more efficiently used. And another thing is that in terms of implementation, the OFDM allows you a very simple, just one tap frequency domain equalizer. Okay, this is a very nice thing. But there are also bad things. And Yeah, this is the biggest concern of OFDM. High peak to average ratio. Okay? Why do we have this problem? Go back to this one, right? The main problem comes from the IFFT structure. Okay? Let's say you have some time domain samples, the frequency domain samples, going to time domain, going to FFT, then you have time domain. Now in the worst case, maybe extreme case, let's say you have all same value, like 1, 1, 1, everything is 1, let's say. That's your original data. Okay? This is a BPSK, and our information is all 1, so therefore you modulate it, after that, still you get all 1. Suppose that's the case. You have all 1 value, go to the IFFT, the time domain sample, what do you have? In frequency domain, you have a flat, all 1, so flat. In time domain, you probably have impulse, right? Impulse like this. Well, of course, you probably don't have impulse because this is a discrete system. What you have actually is that since you have n different subcarriers, if you have all 1, then what you have is that the first one you get n, summation of all this, n. All the other, all 0. Okay? So if you think about that one, right? This is n, so big. All the others is 0, nothing. So think about the difference, the power difference between this one and this one. That's so big. Because eventually you get these time domain samples and you make serialize of all these things, right? So the first bit comes first, the second one comes next, like this, right? Eventually the transmission is all serial fashion. So the first sample goes to here, that sample is this big. Second sample, the rest of the sample is 0. So suddenly big one and all the other 0. Okay? That's what we are transmitting. That's a big problem. You don't want to do that. Okay? Why is that? What's the problem of that? In your transmission, right, in your cell phone, let's say, what would be the most expensive device, component in your device? Some of the RF component, okay? And one of the actually major RF component is a power amplifier. Why do you need power amplifier? Because you do some baseband processing like this, right? These are all the baseband processing. Once you do that, now you have to transmit. Okay, transmit, and that transmitted signal should be delivered to the base station. And in order to make this signal go to the base station, you have to transmit with very high power. So power amplifier is simply amplifier. You are amplifying your original signal, right? After this, we don't have that in picture. After this, all these things is a baseband processing. Once you do that, then that signal is now being amplified, okay, and then transmit over the antenna. So once you have very big sample and all the other sample is 0, if you have such things and that signal goes into the power amplifier, always the power amplifier has some linear region, some limited linear region. But suddenly, one of the samples is so big and the other sample is so low, then power amplifier cannot do that, cannot amplify with the same gain. Okay? What we want is that with the power amplifier, you want to amplify the signal with the same gain. That way, you still keep the same shape of the signal. Only the signal is now amplified. You don't want to make the different shape after amplifier, right? Because of that, typically when you have this high power and the other is a low power samples, your output signal is distorted. Okay, because of a power amplifier. So therefore, this high peak to average ratio is a so big problem for mobile devices. Base station, they don't have this problem generally, but they are less sensitive to this problem. But in mobile station, this is a so big problem. So therefore, but OFDM has this problem. This is not solved. A lot of people actually try to solve this problem. There are so many research papers about this. So many people looked at this problem and still ongoing, but so far it's not clearly defined. Not the best solution is known. Still remaining problem. But OFDM, you have this problem, unsolved problem. So therefore, WiMAX, right? WiMAX is one of the cellular system using OFDM. They use OFDM for downlink and uplink. Okay? This problem affects uplink, right? Because your mobile transmits some data, and that transmission goes through this peak to average power ratio problem. That's uplink. Downlink, you are nothing to do with this problem. Maybe base station has this problem in downlink, but downlink is very less sensitive to this. So no problem on the downlink, on the base station. But in mobile station, you have this problem. So uplink is our concern. So therefore, in LTE, the newer cellular standard based on OFDM, they use this technology, single carrier FDMA, instead of OFDM. Okay? In LTE, this is the technology for uplink. So this is a simple picture of single carrier FDMA. Okay? This picture actually shows pretty similar to OFDM. Okay? This one still has IFFT. Okay? Still have a modulation for each of them independently. You still have a serial to parallel, same for encoder. Looks pretty similar. What is different from the OFDM is that in this case you have additional block called the DFT. Okay, we have a DFT block. That's additional stuff, and a little bit additional is the subcarrier mapping. We have these two. This is a new block, but fundamentally this one looks almost the same as OFDM. So let's say, why do we need this? Well, initially, you start from encoder, okay, and then you do the signal to parallel. But you see here that we have the block size of L, okay? What is L? L is the number of subcarriers that you use. We are talking about the multiple access scheme, right? This is a frequency division multiple access, okay? So since this is a multiple access scheme, I'm not using all of the subcarriers, right? Scheduler will tell me how many subcarriers do you use, okay? So that is L, okay? I can use L number of subcarriers, okay? The total number of subcarriers is N, but I can use only L subcarriers. Since I use only L subcarriers, I have only L data, okay? And each of these L data is modulated, okay? And then I have L number of symbols here. This L size symbol goes into DFT, which has L point DFT. The size of DFT is L. Okay? Of course, the output definitely is L also. You have L sample. DFT is trying to convert from time domain to frequency domain. So in this case, we start from time domain. You have L time domain sample that goes into DFT. The output will be another L frequency domain sample. Definitely L is less than N, right? N is the total subcarrier, and L is the subcarrier you can use. And after you get the frequency samples, L number of frequency samples, right? Now you are going to map this L data into your subcarriers. Base station scheduler basically tells you that, okay, you can use L subcarriers and which L you can use, right? Base station can tell you. Okay, base station told you that you have to use from this one to this one, L subcarriers, right? So what I need to do is that I go through the DFT and get the L frequency samples, and I have to map it into the right location of L subcarriers. That's a subcarrier mapping. Then what happened to the other subcarriers? That one I put it 0. Okay? 0, 0, 0, 0. All the other subcarriers that I don't use, I put the zeros. Okay? And then what I do is that I do IFFT. Because here I was in the frequency domain, Now I need to go back to the time domain again. So I take another process of IFFT, same as OFDM. Then you get the time domain samples of all these, each one for different frequency, and then you transmit. Okay, simply speaking, additional step is DFT. That's the only additional step compared to the OFDM. Okay, but what is interesting here is that this one we call as IFFT. This is called the DFT. You know the FFT is the same as DFT, right? Mathematically, FFT is a efficient computation of a DFT, right? So DFT and FFT is the same, basically. Then why do we call this one as a DFT and this one is IFFT? The reason is that this IFFT has a size of n, and typically n is 2 to the power, like 1024, 2048, right? So for that value, for that n, we can use IFFT, FFT structure. However, this one, right? Look at the size of the FT. This is L, because this L is a number of subcarriers. This L can be anything. It can be 1, it can be even 2, 3, or any maybe prime value, like a same, 7, any value. So if you want to calculate the DFT of the random, arbitrary value, you cannot implement FFT. FFT is typically only possible with some number, right? Not any number, right? Think about the DSP. You learned the DSP, right? Typically, they use a radix 2, radix 4, some split radix. So there are certain way, but you cannot really implement FFT for any number. Okay, there's a certain limitation of the size. Okay, so therefore, this is DFT, because this one should work with any size. Another thing, you know that the DFT or FFT, functionally it's the same thing. DFT, FFT, and IFFT is inverse, right? They are inverse each other. Okay, so now it's interesting because we do FFT or DFT, and later we do the IFFT, and these two actually are inverse, which means that they should be canceled out, right? Because those are inverse, right? Functionally, this is a FFT, IFFT, they will be canceled out. So what happened? Why is not canceled out? That's because these two are in a different size. If these two are exactly in the same size, right? This is n, and this is another n, then definitely they will be canceled out. They are exactly inverse. But these two are in different size. DFT is smaller, much smaller than IFFT. So therefore, these are not canceled out. However, these are not canceled out. However, we see an interesting property called single carrier property. This is why we call this system as single carrier. Okay? Someone actually asked me that, why do we call this one as a single carrier FDMA? Single carrier. It doesn't look like a single carrier, right? We have FFT structure, so therefore we use multiple carrier like OFDM. Structure looks like OFDM, but why do we call that as a single carrier? That is the question that a lot of people asked, and I'll show you the reason why. This is some observations. The observation is that unlike OFDM, in single carrier FDM, the data is originally in time domain, okay? And the size of IDFT, DFT is based on this, and this one is all I talked about. Let me go to the next slide. Okay, this is why we call it a single carrier. Look at the single carrier property. This is a simplified picture. Okay, I only look at the DFT and IFFT part. Okay, and let's say L is smaller than N. There are two different ways of making the subcarrier mapping. One is that you can, when you do the mapping, you have L value. You can map the L value into a certain location of frequency, like this. They put all together consecutively and then put it into certain location, maybe here somewhere or some other, but they all together. That's what we call a localized mapping, because they all together. That's one way. Another way to do a mapping, I'm talking about this subcarrier mapping. Okay? Another way to do a mapping is that you have L number of samples here, and L number of samples you are actually allocating in an equal distance, like this. Right? First sample goes to somewhere here, second sample goes to somewhere there, but each of them is now equally distanced, equally spaced. Okay? This is called the distributed mapping, because you are basically distributing. Right? In that case, you have some number of zeros between each of these red one. Right? So this is a distributed mapping. We can think about two different ways of mapping. Okay? Of course, there are many other mapping, but I'll tell you why we are talking about only these two. Let's think about the first one here. Okay? Localized mapping. This is a little bit easier to understand. Now, let's see that you have a frequency samples here. Forget about DFT. Okay? Now you have a L number of frequency samples. Okay? These are the frequency samples. And then you put all zeros here, right? And then go to the IFFT to get the time domain samples. What happened? This is a question. What happened if you do it? Let's say generally in signal processing, you have some number of samples in frequency domain. You put zeros in the frequency domain, right? You increase the number of samples. Simply do a zero padding. And then go to the time domain. Then what happened? What happened is that this was original signal, right? And you do this whole thing, right? And then in this case, right, this is original thing here. This is time domain. So you see this signal right here in time domain. What you do is that you go to frequency domain and do a zero padding and come back to time domain. Okay? You do the zero padding in frequency domain. Then what happens is you are doing interpolation. You still have the same number of samples, right, in the frequency domain. You didn't change anything. So your frequency response still maintained. Okay? Your time domain envelope is still maintained. Only thing is that you added some zero padding. Therefore, you have more samples. Go back to time domain. You simply have more samples in the same envelope. So that contributes to a interpolation. So this is the output. This is the input here. And this subcarrier mapping, let's say you do this way. You simply do the zero padding. Then the output will be interpolation. You know, in signal processing, same thing happens, right? Let's say you have a frequency domain sample. Okay? And then you do a zero padding in frequency domain. Come back to time domain, you have interpolation. So one domain in zero padding, the other domain interpolation, right? In signal processing. This is one way. So now you see that this is the input, that's the output. So we keep the same envelope. That's the main difference. What happened to OFDM? OFDM, you didn't have this, right? You didn't have this one in OFDM. So therefore, in OFDM, whatever signal you have here is completely different from what you have at the output. Okay? Here, in OFDM, right? Forget about this one. In OFDM, you get all 1. The output is like a n all 0. That's the output, right? Remember? That was the case on OFDM. But in this case, in single carrier FDMA, you have all 1 here. You get all 1. Not all 1, maybe all the same value. Okay? That's the output. That's why we call that as a single carrier property. It looks like a single carrier because whatever your envelope looks like, input, you get the same envelope as output. Okay? Looks like whatever you have here, exactly you get the same thing. That's a single carrier, right? That's why we call that single carrier. You keep the same envelope. Now let's look at the second way This is distributed mapping. Here in the subcarrier mapping, you can do it this way. Okay, insert some of the zeros. Now then, going back to the signal processing knowledge, let's say you have some frequency samples, right? And then you do insert some of the zeros in between its samples in frequency. Therefore, in frequency domain, you have more samples because you insert zeros in between. That's what you do here, right? Then what happened in the time domain? And then you go back to time domain. What happened is that you have repetition. Okay? If you insert the zeros in frequency domain, okay, come back to time domain, your original time domain signal is now repeated. And how many repetition you have depends on how many zeros you inserted. Okay? If you inserted L zeros, you have L repetition. That's the basic relationship between the time and frequency domain. Okay? Even this one, you see that your envelope still maintained. This is not interpolation, this is repetition, but still the envelope is still maintained. This envelope appears multiple times. So from the peak to average power ratio perspective, there's no peak, there's no zero, right? Your original envelope still maintained. Okay? That's the nice thing about these things. Now then, what happens if we use another mapping? Let's say you do a mapping like some number goes here, some number goes to some other random location, right? And you put some zeros in between, some random number. If you do kind of random mapping, this single carrier property is now broken, right? You cannot keep the same envelope. Now it's going to be random. Your output is going to be some random signal. Okay? We don't want that because the fundamental reason that we want to use this technology is because of this nice feature. We can keep the single carrier property. That's why you don't want to allow a random mapping. You can do it, no problem. But if we do that, then our fundamental reason of doing this technology is gone. So therefore, you want to keep it this way for mapping. Okay, I think that's it for today. Any question? Okay, then see you next week.